टॉवल तो ले लें चद्दर भी है इसके अंदर। अब जरा ऐसे ये खुल गया, ये लिंक भी हो गया, ज्वाइन भी हो गया। सिर्फ आवाज बढ़ा दे या तो वो अभी ज्वाइन।
Uh, so we'll start. Sorry for the delay. My laptop hanged, so I couldn't share the screen. Uh, so this week it's regarding the zeroth law and first law of thermodynamics. So the previous week we studied about the type of system. We saw an isolated closed system or an open system. We saw what are states, what are properties. So these are just the properties of system and how to look at the systems as such. So now what the system goes through and in the process what happens. So these are all governed by the laws of thermodynamics. So we'll see there are we'll see till second law of thermodynamics. So this week covers only zeroth law and first law. So in zeroth law, just a second. So in zeroth law, we basically you come across it when you have a fever or something, you put a thermometer. So there the temperature you should read. There you are seeing zeroth law of thermodynamics. So it states when two bodies are in thermal equilibrium. In thermal equilibrium means you are both at the same temperature, and if you have third body, you say it's in equilibrium with the other. So the first and third will also be in equilibrium. So it's basically to govern to estimate the temperature, you can say, because that will be give you an idea of the energy. So where you're putting up a thermometer, so there you are making the thermometer come into equilibrium with your body. So there to measure the temperature. So that's an example of zeroth law of thermodynamics. And then going to first law says that when a process is a cyclic process, so it's like you start with a state and you come back to that state again. So it's like staying you are in ground floor, you go back to the first floor via some way and you come back to the ground floor. It's like a cyclic process, right? It doesn't matter how you go, but you reach the same state again. So that is a cyclic process. In that cyclic process, it says the net amount of heat which is supplied and the net amount of work which is done on the system will be equal. So that's what the first law says. And an extension to that is you define for a simple process. So it says your difference in heat transfer and the work transfer will lead to the change in the internal energy of the system. So these are the basic ideas of the zeroth law and first law of thermodynamics, and we'll see some examples on related to those, majorly dealing with the first law of thermodynamics. So, and we would have also seen how work done is calculated. So work done, you generally integrate, as previous definition with work done is seen. Any thing will be converted to a raising a object. So that is how work is defined. So in that sense, you take into account a piston cylinder arrangement, and a force is applied, and piston moves by some distance x. So you integrate work is force into distance. So in this case, and then you integrate it over the process from start to end. So that will lead you can derive that it's equivalent to pressure into the change in volume. So your work done can be calculated as integration of P dV. So based on that, we will have a first question. It says, in a free expansion process, choose a statement for heat and work transfer. Say the total work done is 0. B, the total heat transfer is 0. C, work done is 0 but heat increases. D, both statement A and B. So what do you think? Free expansion is nothing, there is no obstruction or any restriction for the process to do. So like you have a vacuum, you puncture a gas, or you have a cylinder, you make it expand in the vacuum. So now, because it's in vacuum, you have no obstruction for the gas, so it will be expanding freely. So what will happen in that process? So the answer is option A and B. So here there is no heat transfer happening because it's just the expansion process, and you are not adding any heat or you are not any taking away any heat. So heat transfer will be 0. And second case, the work done is 0. Why is work done 0? Just now we saw P dV, right? There is change in volume. So there should be some work done, right? But this is 0 because you don't have any restriction. It's moving freely. You see, there is no work transfer happening between the surrounding and the system. If you see just the gas as a system, the system is not putting any effort to move into the surrounding. It's not creating any work there. There should be some. It's just like friction for any or you have a car, you do some work to overcome that, and also to you assume that you have body your car is at constant velocity, so you are not doing any acceleration, because so there will be no force required to accelerate it. So your force should be constant. You should not be applying any energy, right? So but your car needs energy to run at constant velocity, that to overcome the friction. So here there is no such opposing force which is happening for the gas. So hence your work done is 0. It's because it's moving freely. So hence both statement A and B are true. I hope this is clear. Okay. So next question is, on a hot summer day, a student turns his fan on when he leaves his room in the morning. When he returns in the evening, what will be the room's temperature? Assume all the doors and windows are kept closed. So and either this thing we can think that it's also insulated. The room is also think the room is closed and it's also insulated. So it's easier for you to understand. So your only means of this thing, your fan is running, your room is all closed, and just the electrical supply is there, and you are plugging in the fan and the fan is on. So what do you think will happen? Will the room will be cooler? Will be warmer? There will be no change, or D, unpredictable? So what do you think will be happening? Is this the first law? If you think in terms of first law.
Room will be warmer.
Yeah, true. Because this room is a closed system now. You only there is no mass transfer happening. So what is inside it's there it's still intact, and because they have said that the doors and windows are all closed. So only electrical energy is coming in, but nothing is going out. So in the process, you are adding some energy to the room, but nothing is leaving. So it will raise the internal energy of the system, right? So internal energy of the room will go up. So how will it go up? So that internal energy can be defined mass into CV, specific capacity volume process, and into delta T. So MCV delta T. So your delta T will increase, right? Because your energy is added, so temperature will rise. So your room will become warmer compared to the previous in the morning. So this was a case where the fan was running. What do you think will happen when refrigerator is on and you open the door? Now the refrigerator is running, and because it's cooling, you think this thing will be cooling. So what do you think will happen when a refrigerator is on with the doors open? A similar question. There the fan was on, now your refrigerator is on, but the door is open. So here too, you see, there is no need to see what is inside. Just see the room. Your inside room.
Option C.
Okay, I'll see. Now you see just the room. You forget what is inside. What are the energy which is coming in, and what is going out. Just like the
I-
previous case, there is no energy which is going out, but there is electrical energy coming in. So what do you think will
yes,
happen? So here too the room will become, the temperature of the room will gradually increase. Uh, First we will see in the first law point of view, and then we will see why it's happening. So from the first law, just the same reason as was the previous case. So here too you have a refrigerator open. You have a room where you are supplying electrical energy to run the refrigerator, and there is no energy which is going out. So your internal energy will increase. In that point, your temperature should increase. So that is one. The other way of understanding is, once you go in the system from the course, throughout the course, at the end you will also learn about some refrigerator Carnot's after the second law of thermodynamics. So you'll learn about refrigerators. So for now you'll see practically, you have a refrigerator, you have the inside will be cold. Have you all seen what will happen at the behind of the refrigerator? Have you ever been near the refrigerator or touched refrigerator outside and behind or something? It will be warmer. So this, even though this thing is refrigerator is inside is cold, outside will be warmer, and this amount of heat which is the refrigerator puts out will be more compared to what the cooling it is providing. So that all we will see later. So hence your room will become warmer. So the main to analyze the system, you think it from the first law of, point of view. This will become more clearer when you go ahead learning the second law of thermodynamics. So even though refrigerator is you are thinking it's cold, but some energy you are putting into the room, so the room will become hot. So answer is option A. I hope this is clear.
yes, clear.
Okay. Sorry, did you ask any question? Okay. So we'll move ahead to the next question. So you have a gas piston cylinder assembly which undergoes an expansion process. So the relationship between pressure and volume is given by PV raised to power n is constant. So that is the process through which the piston is expanding, and the initial pressure is given as 3 bar. So initially the piston, your cylinder, there is a 3 bar pressure, and the initial volume of the cylinder with the piston is 0.1. So after expanding, the volume is becoming 0.2 meter cube. So now they have been asked to find out the work of the process. So for 3 cases, one n is 1.5, b n is 1, and c n is 0. So PV raised to power n 1.5, you call it polytropic process, and PV n 1 is it will become an isothermal process actually. And when n is 0, so V raised to power 0 is 1, so P is constant. So third case, your pressure is constant. So basically I have been asked to find for 3 processes. One first is polytropic, second is isothermal, and third is in constant pressure process. So these are the 3 n values, and we'll see how to solve this. As we have already seen, work done is given by integration of P dV from V1 to V2. So W is nothing but integration of P dV from V1 to V2. So we know V1, we know V2, and we know the relation between pressure and volume. So P is, you can write P as PV raised to power n is constant, right? So we can write pressure as constant by V raised to power n. So we substitute that in terms of P, and now your expression is in terms of V. So variable is V, and you have to integrate it with respect to V. So we can integrate it. So constant you can take it out. So integrating, you will get V raised to power 1 minus n. So by 1 minus n. So this we have to apply it between V1 and V2. So we substitute V2 and V1. So we will get constant V2 raised to power 1 minus 1 minus constant V1 raised to power 1 minus 1 divided by 1 minus n, 1 minus n. So this is applicable only when your n is not equals to 1. You can apply it for n equals to 0 also. So you will get the same, P equals to V2 minus V1. So in that case, except n equals to 1, you cannot apply. If you make it n equals to 1, then it will be constant by 0. So that's not what will happen. So we will see how to solve n equals to 1. For now, you can substitute n equals to 1.5. So substituting that, we can find out, except constant, we can find the other terms. So now to find out constant, what we can do is, we know the relation P1 V1 raised to power n equals to constant. So we can substitute P1 V1 in terms of constant. So and we know the initial pressure, it's 3 bar, and initial volume is 0.1 and final volume is 0.2. So instead of constant, we can write P1 V1 raised to power n. So n is 1.5, and we know all the values. We can substitute and we can find out how much work is being done. So it will come out to be 17.6 kilojoule per kilojoule. The other way of finding is, here they have used P1 V1 raised to power n equals to P2 V2 raised to power n, and you can find out, you can substitute that also. So here now for how to solve for n equals to 1. So I hope this is clear when n is 1.5. Here they have substituted constant as P2 V2 raised to power n and P1 V1 raised to power n. So now it's the expression comes down to a simplified form, P2 V2 minus P1 V1 by 1 minus n. So and then they have using the same relation, they have found out pressure, because you know pressure 1 P1 V1 V2. So we can find out the P2 and they are substituted again. The other way is to, you can directly calculate constant, you know P1 V1. So you can directly use that and substitute that constant value, and you can find out the work. So it's both ways you can solve that. So now when n equals to 1, so we'll go back again to the previous work expression. So work is integration of P dV. So now n is 1, so PV equals to constant. So you can write pressure as constant by V. So you take constant out and integrate with respect to V. So for that, you'll get ln V2 by V1, and constant is nothing but P1 V1. So the work will come out to be P1 V1 ln V2 by V1. So now we know all the values. We know P1 V1 and also V2. We can substitute all. So P1 is 3 bar, V1 is 0.1 meter cube, and you're converting bar to Newton per meter square. So it will be 10 power 5. 1 bar is 10 power 5 Newton per meter square, or 10 bar 5 Pascal. 1 Pascal is 1 Newton per meter square. So 3 bar is 10 power 5 Newton per meter square, and then we want this to be written in kilojoules. So we are dividing by 1000, and V2 is 0.2, V1 is 0.1. So substituting that, we will get work as 20.79 kilojoules. So now the other third case was to find out when n is 0. When n is 0, we saw that the expression comes down to be P equals to constant. So when pressure is constant, it's easy. You take it out, integration will be P integration of dV. Integration of dV is nothing but change in dV, change in velocity, change in volume. So P V2 minus V1. So the simplest this thing. So we know pressure V2. So pressure will be same. So P equals to V2 minus V1. So P is 3 bar, 3 into 10 power 5 into V2 is 0.2, V1 is 0.1. So it will become 0.1. So 3 into 10 power 5 into 0.1 divided by 1000 to make it kilojoule. So it will come out to be 30 kilojoules. So The other, if you see in the pressure volume diagram here, so you have all the three processes listed here. So the integration of P dV, what it says is area under the curve. Integration in along the curve, it says the area which the curve makes below it with the x coordinate. So here this is volume. So the shaded region is the area which the curve makes. So that will be equal to the work. So graphically, that's the idea what the work gives along the process in the PV diagram. And similarly, we'll see in after second law, we'll see that heat also can be found out from the area. There, it's not in the PV plane, but it's in the temperature entropy plane. So that we will see in the coming weeks. So for now, the area under the curve in the PV plane, it's denoted by the work. So 1 to 2A is your process 1, and then 2B, and then 2C is your pressure constant. So you see that will takes the maximum work which is given by the process. So here if you see the pressure is constant, so that is the third 2C. So done. So moving on, it's a simple problem on the first law of thermodynamics. So we know we saw that when a process goes through a cycle, so your net Q transfer, heat transfer, and net work transfer will be equal. So here they say a closed system evolves from an initial state 1 to a state 2 along the path x. So listed here, first row. So you have two separate processes. You will see the first table. You will see first table. So here the path 1 to x is how the initially the process happens, and they say it then comes back to state 1 following two different paths. So they say it goes, it does a process x from 1 to 2, then it can come back from 2 to 1 along two different paths. It can come along y or it can come along z. So that's what they say. They can come back along two different paths y and z. They say during this process the system transfers work and heat energy with its surrounding. So you have both work transfer and heat transfer. So they are listing out heat transfer which is happening during the process and work transfer which is happening through the process. And we need to find or estimate what will be the work or heat transfer where a question mark has been put. So we'll see first case, it goes from 1 to 2, so there is a minus 10 of heat transfer, and then we'll see it will come back from 1 to 2 along path y. So minus 10 plus 7, so it will come out to be minus 3. So the system is rejecting some heat to the surrounding. So minus 3 kilojoules, we'll say kilojoules. So minus 3. So this should be equal to the net work transfer, because this is going through a cycle. It's coming from 1 to 2 along x and then going from 2 to 1 along y. So now the net transfer should also be equal to minus 3. So we'll assume this 1 to 2 W, so W plus 4. So your W will come out to be minus 7. It's just a simple expression. I think I'll have to write it somewhere again. So you're this thing at 10 minus 10 plus 7 equals W plus 4. Is the screen visible? Can anyone say what I am writing, is that visible or just the slides visible? okay, anyway, so your W will come out to be minus 7, and then through 2 1 there's another question mark there. So here initially that 1 to 2 there is a minus 10 plus Q, we'll assume Q, which has to be found out for process 2 1, process Z. So now we know that initially the work was minus 7. So now minus 7 plus 8, so it will be minus 1, and we have minus 10 plus Q equals minus 1, equals 1, minus 7 plus 8, so 1. So minus 10 will come here, so it will come out, it will become 11. So X is minus 10 and the process it will be minus 7. So initially we found out work using process X and Y, and then similarly we found out using X and Z what will be the heat transfer in process Z. So same approach here in the second problem also, so you can try that out. So you see Q plus 4 equals minus 7 plus 9, so it will be 2. So you can take 4 on that side, Q becomes minus 2. So initially path for 1 2 it will be minus 2. So again we know minus 2, so for 1 2 X and Z, so minus 2 plus minus 10, so it will become minus 12 equals minus 7 plus W, so it becomes minus 5. So that's, there's nothing, you have to just take two, you have two equations, you have to solve both Q and W. So and your you have to use first law, because this is going through a cycle, your the internal energy change will be 0, because that's a state variable, and so your Q net will be equal to W net. So that's the approach you have to use to solve this. So moving on, we have air contained within a piston cylinder assembly which is slowly compressed. So as shown in the figure, so during the first process the pressure first varies linearly with volume. So as shown in the figure 1 to 2, so you see there is a linear variation in pressure with respect to volume, and then remains constant. So after that it's remaining constant. So determine the total work in kilojoule. So we saw the previous problem, right? So where there we saw we can find out using the work done as the area under the curve. So now this process has been represented graphically in a pressure volume diagram. So PV, you know pressure values, and volume you also know. So you have to just take the area under this curve, and that will be equals to the your work done. So from 1 to 2 it's varying linearly, so you have to, you can split this into 2. So you can split as a triangle, and then at the bottom part we will have a rectangle. So area of the triangle is half of your height into width. So width will height into base. So base will be nothing but the change in volume. So 0.07 minus 0.055, and your height will be P2 minus P1. So that, and also the bottom one will be your pressure 1 into change in the volume. So the other way of writing this whole for the process, linear process 1 to 2, including that triangle and rectangle, is the expression here P1 plus P2 by 2 into V2 minus V1. If you add these two areas, this is the expression which you will get. And from 2 to 3 is a constant pressure process, so your P will be remaining same into, or the area, so 0 minus P3, so that will be equals to P3 into the change in volume 0.055 minus 0.015. So that's what the expression here on the left says. So work is P1 plus P2 by 2 into V2 minus V1. So that is the area under the curve for process 1 2, and plus P2 V3 minus V2, because pressure 2 and pressure 3 are same, so you can express as P2 or P3. So P2 into V3 minus V2. So that is the area of the rectangle, or the area of the curve under process 2 3. So now you know pressure 1, pressure 2. Pressure 1 is 100, pressure 2 is 150. We know V2, V1, V3, 0.07, 0.005, 0.55 and 0.015. So you have to just substitute the values here. And pressure, this is given in kilopascal. So kilopascal we are converting it to Newton per meter square, or 1 Newton per meter square is 1 Pascal. So this will be 1000 pascals, or 1000 Newton per meter square, and dividing it by 1000 to make it into kilojoule work. So substituting that, we'll get for process the work done is minus 1.875 kilojoules, and in process 2 3 the work done is 6 kilojoules. This is negative because we are doing, it's a compression process and we are giving work to the system, hence this is negative. So that's what indicates. You substitute that V2 minus V1, so we will know, based on this you get a negative. The negative sign indicates it's in compression process, so you have to do work to the system. So the overall work which is done on the system is minus 7.875 kilojoules. So this is the work which is going into the system for compression. Clear? Any doubts on this? Okay. So moving on, we have a carbon monoxide gas which is contained within a piston cylinder assembly. It undergoes 3 processes in series. Process 1 2, which is a constant pressure expansion at 5 bar. So P1 P2 is 5 bar. From they have given 0.2 to 1 meter cube. That's the expansion process which is happening. So after that, 2 to 3, it's a constant volume cooling. So during constant volume, it's been cooled from state 2 to state 3. So now the pressure P3 is 1 bar. Then again, if from 3 to 1, you are compressing from state 3 to initial state. So during which the pressure relation is PV equals to constant. So this is an isothermal process, PV equals to constant, and we know how to calculate work for an. We have already seen in the previous problem how to calculate for PV equals to constant, and then also you know for 1 to 2 work done. So we have been asked to sketch the process in series on a PV coordinates and evaluate the work for each process. So that's what it's been drawn here. So in a PV coordinate, they said 1 to 2 is a constant pressure process. So from 5 bar pressure at 5 bar, it's expanding from 0.2 to 1 meter cube. So it's going from 1 to 2, it's an expansion process. And then from 2 to 3, you have a constant volume process. So that's what they say, and it's coming down to pressure 1 bar. So from 5 to it's coming to 1, so 2 to 3, and then it's going back again. Again to 5 bar, to the initial state where it started from. So now and evaluate the work for each process. So that's here. I think you can try this one, because we have seen how to solve for each of the processes, how to solve this. So I'll give you some 2-3 minutes. You can solve how to see how what you get, and you can verify whether the values are same. Hello, yes, man. Yeah, yeah, I'm there doing class. So we have, constant process. You can it's just P into dV, so that you can easily find out. And process 2, 3, there will be no work done because your pressure is changing, but your volume is constant. And here also they say it's a cooling process, so there is no heat work transfer happening. So if you integrate P into delta V, your delta V is 0, so your work done will be 0. And then 3 to 1 is isothermal process. You have already seen PV equals constant, so there 1 by V into dV you get ln terms, so P1 V1 into ln V2 by V1. So you have to just substitute those values. So this is all we have seen. Constant process 1 to 2, it's a constant pressure process. So P dV, so P1 is 5 bar, V2 minus V1, so 5 bar into V2 is 1 meter cube minus 0.2 meter cube into bar, so 10 per 5 Newton per meter square, and dividing by 1000 to make it kilojoules. So it will come out to be 400 kilojoules, which the system is doing. So it's an expansion pressure, you are getting 400 kilojoules of work. So now then process 2 to 3 is a constant volume, so piston does not move, so your work will be 0. Then we have process 3-1. In process 3-1 your it goes by PV equals to constant. So you can after integrating you will get P1 V1 into ln V1 by V2, because this is going from 3 to 1, so it will be V1 by V3. So substituting that 5 bar, P1 is 5 bar and V1 is 0.2 into ln 0.2 by 1 meter cube, and this is bar, so again multiply by 10 power 5 and dividing by 1000 to make it kilojoules. So it will come out to be minus 160.9 kilojoule. So here you have to do work to compress it from 1 meter cube to 0.2 meter cube. Along there will be PV equals to constant relation or an isothermal process. So you have to do minus 160.9 kilojoule. So now the net work is summing up all three processes, you will get the net work which is being done. That will come out to be plus 400 plus 0 minus 160.9, which is 239.1 kilojoule. So this is the amount of work which you are getting with the cycle. So if you do such a cycle, so you are producing 239.1 kilojoule of work, and this will come out to be the area under this 3 process. So area under the, if you see it's not a triangle but something like that, so it's the area of that which will be equals to this net, W net. Because if you see 1 to 2 you are getting work and 3 to 1 you are rejecting, so 3 to 1 is the area under the curve which is getting subtracted from the area 1 to 2. So the area under the enclosed by these 3 curves is what will be the net work, so W net. Okay, is it clear? Any doubts? Okay. So moving on, we have another piston cylinder assembly process. The gas undergoes a cycle in a piston cylinder assembly consisting of the following 3 processes. So process 1, 2, we have a constant pressure process for 1.4 bar, and we have volume, initial volume, it says 0.028 meter cube, and then the work done in process 1, 2 is 10.5 kilojoule. Then process 2-3, we have a PV equals constant relation process. So there they are saying that internal energy U3 and U2 are constant. So you see U3 equals to U2, you write the change in internal energy is 0. So internal energy is 0 is nothing but your delta T is 0. So your temperature is constant. So that will be an isothermal process. That's what I am saying. Compression with PV equals constant is isothermal process. Then process 3-1 is a constant volume process, and they are saying that internal energy change is minus 26.4 kilojoules. They are saying that there are no significant changes in the kinetic and potential energy, so you can neglect kinetic and potential energy change of the system. And then sketch the cycle on a PV diagram. Then part B is calculate the net work for the cycle, just like the previous one, and calculate the heat transfer for process 1-2. So you have to find net work done and the heat transfer happening between process 1-2. So now I'll see how to do that. So here it's a sketch of the process. So this is initially pressure 1.4 bar, so constant pressure process initially, so it is at 1.4 bar. It goes from 0.028 meter cube, and it produces some work of 10.5 kilojoules, and which is state 2. So we don't know what state 2 is, but the area under this curve should give you 10.5 kilojoules. Then from 2 to 3, it says it goes from a constant temperature isothermal process, or U3 equals to U2. There is a constant internal energy process. U3 equals to 2 to 3, and then from 3 to 1, they have given it's a constant volume process, and your change in internal energy is minus 26.4 kilojoules. So that's what is being listed here. So we have plotted all three processes here, and now we have to find out the net work of the cycle and then heat transfer in process 1-2. So for this we need not to find 1-2 work done, we already know work done in 1-2, and 3-1 your work done will be 0. So you have to just find out work done in process 3-2. So process 3-2 can solve. So work done 1-2 we know 10.5 kilojoules, and 3-1 is 0, constant volume process. So W23 is, we already know how to the expression for an isothermal process, or PV equals to constant. So PV into ln V2 by V3 by V2, or P2 ln V1 by V2. So because constant pressures, V3 equals to V1, and we know state V1, but we don't know state V2. So how can we find V2? For that, we know the work done in process 1-2. Process 1-2 we know the work done. So for this you can write the work done will be equals to pressure into change in volume, and you know the pressure, you know the state 1 volume, so you can find out state 2 volume. So work done in 1-2 is nothing but pressure into V2 minus V1. We know pressure, we know V1, we can find out V2. So V2 will come out to be 0.103 meter cube. We know work 1-2 is 10.5 kilojoules, and pressure we know it's 1.4 bar. So substituting that, we can find out V2. So now using this V2, you substitute it in the work 2-3 relation. There we know P1, we know V1, we know V2. So we can substitute that. So we'll get 1.4 into 0.0103, and ln the volumes of the two processes, V1 and V2. Substituting that, you'll get work done is minus 18.78 kilojoule. So now So the total net work done is nothing but sum of these. So it will be minus 18.78 plus 10.5 kilojoules. So this will come out to be minus 8.28 kilojoules. So in this process, if you see, there is a net negative one. So this amount of energy is what have to be given to the system. So you have to supply minus 8.28 kilojoule to the system. Previously, in that process, you saw that net work is positive. So this is the net work done which you are getting from the cycle. Using that three process, you are getting 231 kilojoule of work from the system. So you can use that for somewhere else. Here in the using this three cycle, you have to provide minus 8.28 kilojoule additionally. So you have to supply that work. So that's what this negative says. So the next question was to find out the heat transfer occurring between process 1 to 2. So for that, you can write the first law. So delta U, delta A, change in energy of the system. So E. So there you are asking to neglect the kinetic energy and potential energy. So it will come out to be the internal energy U2 minus U1. So U2 minus U1 equals to Q12 minus W12. So basically, in most of the all cases, you will be seeing that you will be neglecting the kinetic energy and potential energy. So you'll ultimately be left out with internal energy equals to then net difference between the heat transfer and the work transfer. So U2 minus U1 equals Q12 minus W12. And so here Q12 can be written as U2 minus U1 plus W12. So this rearranging, and you also know that PV equals to constant. There we saw that U3 equals U2. So you can substitute U2 as U3. So U3 minus U1 plus W12 equals the Q12. So U3 minus U1 is already given. You see in the process 131, it is 26.4 kilojoule. Here is U1 minus U3. There we want U3 minus U1. So substituting negative. So 26.4 plus work done is W12, which we have already know from the question. It's 10.5 kilojoule. So substituting that, we will get 36.9 kilojoules. So this is the amount of heat which is supplied to the system. So the sign convention, we see heat transfer to the system is positive and work transfer from the system is positive. So that we have to remember. So that is a sign convention basically largely used. So Q12 is positive 36.9 kilojoule. So this is the amount of Q which is being taken by the system. So Q12 is 36.9 kilojoules. I hope this is clear. Any doubts? Okay. So moving on, a certain amount of air is enclosed inside a vertical cylinder. So the bottom cylinder air is shown in the piston arrangement. So there we have a frictionless leak-proof system as shown in figure. So in this some amount of air is enclosed, and then you have a cylinder where your air, you are pumping in some air. So initially the pressure of the air in the cylinder is 60 kilopascal and cross sectional area of the piston is 20 centimeter square. So now the cylinder, what is doing is connecting it to a reservoir. So or else think it like you have a the reservoir is like your cycle tire and this is your piston pump, something like that. It's a similar arrangement, but here you have a piston, this thing you have you are connecting it to a air reservoir. So that's it. So the cylinder is connected through a valve to a rigid vessel which initially contains, so here this is rigid, so your volume will not change. So this is not an ideal example, but you can think that is your this thing is a close there is mass transfer, but your system will not change. You have a closed container where you can put in mass. Your air is supplied, and your this thing volume will not change of the vessel will not change. So this is hence that it's called rigid. So rigid vessel, which initially contains air at pressure of 30 kilopascal. So this vessel contains air at 30 kilopascal, and this piston contains initially 60 kilopascal. So that's what is given. So the lower face of the piston is exposed to the atmosphere at 100 kilopascal. So this piston is exposed to 100 kilopascal. So now if you see, initially the air is at 60 kilopascal and the atmosphere has 100 kilopascal. There is a pressure difference. So because of that, the atmosphere will compress the air inside to make it equalize. So the air will get compressed because of the atmosphere. So now what is done is the valve is now opened. So now when the valve is open, because the piston is being moved by the surrounding, because the surrounding has higher pressure, this air will get compressed and it will move to the vessel. So now because here is 30 kilopascal, so this pressure is lower than here, so the air will start moving. So then the piston slowly moves a distance of 12 centimeter from its original position. So that's what is been given in the problem. So now we have to calculate what is the work done by each of the following system. A, the piston, how much is the work done. B, the atmosphere, because the atmosphere is exerting force on the piston and it's compressing air. And C, the air. So we'll see how to solve this. So initially what we'll do is we'll find out what is the force being applied in the piston. So we'll do what are the forces acting on the system piston. So you have atmospheric pressure acting on the piston. So the force will be pressure into area, the cross section area. So that is the amount of force which is acting on the down phase of the piston from the atmosphere. So P atmosphere into area, cross section area of the piston. This will be equal to the air inside the piston cylinder arrangement that will exert force on the top of the piston. So P into area, cross section area, and the piston will have some weight. So mass of the piston into G, acceleration due to gravity. So now we know initially the cylinder had pressure 60 kilopascal and the atmospheric pressure we know. So we can estimate the mass of the piston. So mass of the piston will be difference in pressure into area divided by acceleration due to gravity. So atmospheric pressure we know it's given 100 kilopascal and initial pressure in the cylinder is given as 60 kilopascal. So this is 40 kilopascal, 40 into 10 power 3, and the area also given 20 centimeter square. So 20 into 10 power minus 4 to convert into meters. So 20 into 10 power minus 4 into 40 into 10 power 3 divided by acceleration to gravity 9.81. So it will come out to be 8.155 kg or kilograms, 8.155 kilograms. So that is the mass of the piston. So we have estimated the mass of the piston. So now it is clear that the piston is moving up. So the piston is moving up from an initial position by a distance of 12 centimeters. So the piston, what is it's gaining some potential energy. So the work done on the piston is it's gaining some potential energy, and because it's moving up, so moving by 12 centimeters, it's gaining some potential energy, and it will be higher than what it was there previously. So that is the work which is being done on the piston. So work will be minus mass of the piston into G into Z2 minus Z1. Because the piston is gaining, taking some work, because it's not doing, but it's taking some work to raise itself to some height. So work is done on the piston. So it is consuming some work from the surrounding. So hence negative. minus mass of piston into acceleration due to gravity and into the distance it moved. So mass we have already calculated 8.155 and into 9.81 into 0.12 or 12 centimeters, so converting it to meters, it will come out to be minus 9.6 joules. So this is the amount of work which is done on the piston. And then what is the amount of work which is being done by the atmosphere? So atmosphere, we have constant pressure and it's moving the piston and changing the volume from V2 to V1. So we know the cross sectional area, and volume can be written as A into the height, right? The height is nothing but the amount with which the piston has moved, the 12 centimeter. So we know we can write A into h, the piston distance moved by the piston. We know pressure, which is 100 kilopascal, so 100 into 10 power 3 into the cross section area 20 centimeter square, so 20 into 10 power minus 4 into 12 centimeters, so 0.12. This will come out to be 24 joules. So this is the amount of work which is done by the atmosphere on the piston or on the system. So 24 joules is the amount done, work done to the system. So next is W air. So W air is your air which is going into the vessel. So there also you see how much amount of volume of air which will go is your what is moved by the piston. That amount of volume of air is what is pumped into the vessel. So that is also will be same delta V, and air 60 kilopascal will remain constant because your valve is opened here. So this thing will be moved and your pressure will be the same. So 60 into your delta V. So that is the amount of work which is being taken by the air to go into the reservoir. So 60 into 10 power 3 into same delta V which was happening in the previous case. So this also here we are doing that the atmosphere is doing some work to transfer that amount of volume of air to the reservoir or the vessel. So hence negative. So 60 into 10 power 3 into your change in volume. So this comes out to be minus 14.4 joules. So if you see now, if you add this 3 up, the net this thing is 0. Why is this 0? Here it's 0 because your atmosphere here is surrounding and your system is just the piston and air which is inside. So net transfer between this thing is coming out to be 0. If you assume just the system which is piston and the air, it's consuming minus 24 joules. So minus 24 joules. It's seeing that 2 points of view. This is, surrounding is doing 24 joules on the system, and the system is taking in minus 24 joules. So that's why it's coming out to be 0. So you are adding up both the surrounding and the system. Yeah, when you consider both just the net amount of the system, hence then you will get the work transfer on the system. So that will come out to be minus 24. So minus 24, it consumes 24 joules of energy to compress the air and move that amount of volume of air to the vessel. So it takes 24 joules. So in part of which is 9.6 is consumed by raising the piston by 12 centimeters. So the 24 joules what is done by the surrounding. So 24 joules is the net positive work which is coming in, out of which 9.6 joule is consumed in raising the piston by 12 centimeters in height, and 14.4 joules is consumed in pumping in the delta V amount of volume of air to the vessel. So that's what this problem we can understand from the work done calculation. Is it clear? Any doubts? Okay then. So moving on, we have a steady state operation, a gear receives 60 kilowatt through the input shaft and delivers power through the output shaft. So for the gearbox as a system, the rate of energy transfer by convection, so heat transfer relation they are given some, so minus H A TB minus TF. So TB is the body temperature of the gear outer surface temperature, and F is the fluid which is there in the gearbox temperature. And they have given both the temperatures, and H is the heat transfer coefficient, so that also they have given. Area is given. You have to just substitute it to find out Q. Just the other way of finding it, the Q. So is the temperature of the surrounding air from the immediate vicinity of the gearbox. From the gearbox, evaluate the heat transfer rate and the power delivered through the output shaft, each in kilowatts. So this is the diagram you can see. So 1 through 1 is what you are giving in some work. So see minus 60 kilowatts. So you are giving in 60 kilowatts of work, and output you are getting W2. So you have to find out how much is the heat transfer and how much is the work done, W2. You can get from the gearbox. And they have given outer surface area. So this gearbox is enclosed and the outer surface area is 1 meter square. So now you assume, you don't think about this gearbox itself, you just see there is a box, you don't know what is there. You see there is 60 kilowatts of work which is coming in and some W2 which is going out, and there is some heat transfer happening from the box. That heat transfer is given by this relation, and we know all the values for the calculating Q. So we have to just substitute in. H is 0.171 kilowatt per meter square Kelvin, and A is 1 meter square, and we know the temperatures 300 minus 293. So Q is 1.2 kilowatts. This is negative because heat is transferred out. If it is coming in, it will be positive. Work coming in is negative. Heat coming in is positive. So it will be other way around. So here Q is negative. So it's heat transferred out, minus 1.2 kilowatts. So you have to just apply the first law. dE by dt is 0 because there will be no change in internal energy. So it will come out to be work done, net work done, it will be equal to net heat transfer. Work done is W1 plus W2 and equals to heat transfer Q. We know Q, we have found out, that is minus 1.2. W1 is minus 60 because it is coming in. You have to be careful putting in sign. W1 is coming in, so work done coming in is negative, heat transfer going out is negative, so both are negative. We are substituting that, and we can find out W2. So that will come out to be 60 minus 1.2. So W2 will come out 58.8 kilowatt. See, this is positive. This means it's going out. So you are getting that work. Work done by system is positive. So W2 is positive, 58.8 kilowatt. So it's a simple problem on heat first law. So moving on, we have a frictionless piston cylinder arrangement shown. A similar problem with the piston cylinder, but here two piston and cylinder which is coupled together. So initially the air contained in cylinder A occupies 0.0864 meter cube and is at 200 kilopascal and 300 Kelvin. While the air in cylinder B occupies 0.0398 meter cube and is at 300 Kelvin. So the cross sectional area of cylinders A and B are respectively we know 0.00786 meter square and 0.00393 meter square. So that is the cross sectional areas of cylinder A, piston A and piston B. Heat is now supplied to cylinder A, causing the piston to move slowly downwards by 2 meter. So now for piston A you are supplying some heat. Because you are supplying some heat, your piston, there will be supplying energy, so energy of the fluid inside A will increase. So now what will do, it will push on the piston and compress the B. So the total mass of the piston and connecting rod is 10 kg. So you know this arrangement of coupling pistons and the rod connecting those two pistons is of 10 kg. Cylinder B is completely insulated. So B is completely insulated, there is no heat transfer happening. Okay, there can be only work transfer. So determine mass in cylinder A, initial pressure in cylinder B, mass in cylinder B, I think mass, I can see, mass of piston, I guess. D is W atmosphere, which is net work which is done on the atmosphere, and then W piston, the piston how much work is done, and final pressure in B, final temperature in B, then work done by in B, and final pressure in A, and final temperature in A, then total heat supply. There's a multiple this thing. We'll see how solve one by one. We'll see how to solve one by one. So we'll start with A. So mass of air in cylinder A. So it's simple. We'll go with ideal gas relation. So PV equals to MRT. So M is the mass. So R here too, you have to be careful here to put in terms of kgs. So R is 288.68 kilojoule per kg Kelvin. So 281 will be kilojoule per kg, kilomole per Kelvin. So here it's in kg. So 288.68. So pressure is 200 kilopascal, which is given, and initial temperature is also 300 Kelvin. And also we know initial volume. So you have to just plug in all values and we can find out the mass. So 0.2 kgs will be the mass. So the first part is done. The next is, the question is initial pressure in cylinder B. So for that what we do is, we will go back to the piston, we will see what are the forces acting on the piston. So you see just the top piston with area A, there from inside your there is some pressure acting on the piston face, and from bottom you have atmospheric pressure acting. So a force will be the difference between these two. So P minus P atmosphere, because A is 200 kilopascal and atmosphere will be at 100 kilopascal. So pressure A is more, so it will push the piston down. So P minus P atmosphere into area of piston, area A, then the mass of the total piston arrangement, which is 10 kg, into G. This will be equals to pressure acting in cylinder B. From inside it will push this, try to push the cylinder up, and from atmosphere you are acting some 100 kilopascal is acting on the piston B top. So P minus P atmosphere into area of cylinder of the piston B. So this is the net force which is acting on the piston arrangement. So from this we know initial pressure P A in the cylinder A and atmospheric pressure. We know mass of cylinder. We also know the atmospheric pressure here and the area of piston B. So you have to just replace it and you can find out the pressure acting on the piston bottom face of piston B. So P1B will be equals to P atmosphere. We are just replacing in terms of each pressures and areas, and then you have to just substitute all the values. So you know APA, piston area A, piston area B, atmosphere is 100 kilopascal, P1 is 200, and then mass of cylinder is 10 kg, G is 9.81, and area of piston B. So it's all substituting. We can find out pressure acting at system. Initial pressure of cylinder B is 325.45 kilopascal. So that is the pressure which is initially there. So now the piston will be at rest because the force will also all be balanced. So that's what we assumed and we calculated the pressure. So initially the pressure B will be 325.45, A will be 200, and this will be balanced. So this piston B has more pressure because of the weight of the piston which is acting on the gas in cylinder B. So okay, so we have calculated that. So pressure we have calculated. So next is mass of air in cylinder B. So again same ideal gas relation. We substitute all three to we know pressure, we know volume, and we know R, we know temperature. So we'll come out to be 0.15 kg. So the next is work interaction for the atmosphere. So what is the work done by the atmosphere? So so it will be nothing but P atmosphere into delta V change, volume change in A and volume change in B. So given that the piston is in the problem, it's given that the piston A moves by 2 meters. So moves down by 2 meters. So delta V atmosphere is minus 2 into A PA, because it's moving down. So your work is done on the atmosphere, and delta V atmosphere is 2 into APB. So here the atmosphere is moving, the piston B is compressing, so atmosphere is doing some work to compress the air in cylinder B. So from there it's negative, from here it's positive. So hence delta V atmosphere, we know 2 meters, so the volume can be calculated using the corresponding areas of pistons. Because the piston is coupled, so what is moved from 2 meters is moved by piston A, same amount is moved by piston B. So substituting this, we can P atmosphere we know 100 kilopascal, and area we know, we have to just substitute, and we can find out that net work done is minus 786 joule. So this is the atmospheric work which is done on the system. Then the piston work is nothing but it is losing some potential energy. So mpg z2 minus z1. So here it's moving by 2 meters. So mass we know 10 into g 9.81, and z2 minus z1 is 2 meters. It will be close to g, I think they are taken as 10, so it will come out close to 200 joules. So at any instant, considering the air in cylinder B as a system, we may write, so for cylinder B, you are applying the first law. So at for any process, your Q is 0 because it's insulated. So that's what is given in the problem. So your change in internal energy will be equal to the work done on the system. So work done we can find out by P minus P dV, and du is nothing but mcv delta T. So now here they are integrating it. So Cv equals dt equals minus RT by V dV. Okay, anyway, so here T you are taking it down, and your Cv can be written as gamma R by gamma minus 1. So gamma is corresponding will be 1.4 for air. Gamma is nothing but the ratio of specific heat at constant pressure and specific heat at constant volume, Cp by Cv, that is gamma. So this is a little tricky, I think. From here you can find out pressure too. Then final temperature is nothing but you can so we'll leave this part. I think this is in coming weeks we can see that. And final temperature B is again going back to the ideal gas relation. So assuming that P to B is given, so we'll substitute that, and you can find out temperature as 327 Kelvin. So if we apply first law, then we'll get is to the cylinder B, we can find out how much is the change in internal energy, and from there we can find out the change in work. We'll equal to m into Cv T2B minus T1B. So we have found out the temperature here, and we have found out initial temperature is known 300. So we will know how much is the work done on the gas in cylinder B. So it will come out with minus 2923 joules. So from above expression, we can again find out how much is the pressure in cylinder A. After coming to equilibrium, after it's moving 2 meter, what is the pressure at A? Again we can do a force balance and we can find out pressure. Now we are finding out for the piston A, so that will come out to be 258.7 kilopascal, and the change in volume also we can find out. So V2 is 0.10212. So from there we can find out the temperature. Again substituting the ideal gas relation, will come out to be 458 Kelvin. So from there we can find out how much is the change in internal energy equals Q minus W. So here there is a heat which is supplied and there is some W which is being done. So that will be equals to the change in internal energy. So previously we saw, assuming both surrounding and system, your net work will be 0. So your piston cylinder A, WA, will be coming out to be the summation of all the other works. So substituting that, and delta U is MC by delta T, we can find out Q, which will come out to be 26.714 kilojoule. It's a big lengthy problem, but the major equations which used are, we used ideal gas equation to find out the mass, to find out the temperature. At a known pressure volume we can find out temperature because the mass is known initially, so we can find out temperature. And other relation is to the find the pressure using the force balance. So this is and the first law. So the major equations which we used. I'll change this and I'll substitute the P2 value directly and remove this portion. So it will be easier for you to go along. Okay, a last and final problem. So we have a piston cylinder device which contains 0.05 meter cube of gas, initially 200 kilopascal. So at this state, a linear spring that has a spring constant of 150 kilonewton per meter is touching the piston but exerting no force. So you have a piston, you have a spring suspended, and piston is just touching the spring. It's not compressing the spring; it's just touching the spring, and you have some amount of gas inside the piston cylinder arrangement. So that is given as 0.05 meter cube, and pressure is 200 kilopascal. Now what you are doing is you are supplying heat. Because your heat is supplied, the gas will be energized and they will start pushing the piston. So now that will compress the spring. So if the cross sectional area of the piston is 0.25 meter square, determine the final pressure inside the cylinder, the total work done by the gas, the fraction of this work done against the spring to compress it. So that is what is being asked. So that process can be represented like this. So from 200 to 320, we will find out the pressure 2, which will come out to be 320, and that's process. So we'll come back again to the graph finally after solving all. So the enclosed volume is at the final state. So heat is transferred to the gas so that the volume inside the cylinder doubles. So you know V2 is 2 times of V1. So V1 is 0.05 meter cube, which will come out to be 0.1 meter cube. So now the displacement is nothing but x is volume is your displacement into area, cross section area. That will be the change in volume. Change in volume is V2 minus V1 will come out to be 0.05. So and we know the cross section area 0.25 meter square. So that is 0.2 meter. So now from this we know that spring, the force exerted by spring is spring constant into your how much length you have compressed the spring. So that for that we have found out the displacement. So that will be equal to the amount by which you are compressing the spring. So now the force exerted by the spring is K into X. So K is 150 kilonewton per meter, which is given, into 0.2 meter, shall come out to be 30 kilonewton. This is the force which is exerted by the spring on the piston. So now we can convert that into pressure. So pressure is force by area. So 30 kilonewton by 0.25 meter square, we get 120 kilopascal. So without the spring, the pressure of the gas would remain constant at 200 kilopascal while the piston is rising. So there will be change in volume, piston will keep on rising, but the pressure will be same. But under the effect of the spring, the pressure rises linearly from 200 to 320 kilopascal. So now, because the spring is compressing it, so the pressure will start rising, and it will rise from 200 to 320 kilopascal. So that so next is to find out the work done. So work done, now we can calculate directly from the graph here. So it's varying linearly from 200 to 320. So can find out it from the graph. So 200 plus 320 by 2 into the change in volume, 0.1 minus 0.05. So it will come out to be 13 kilojoules. So that is the work done. So now the work done in this spring, so that you can calculate by change of k x1 x2 square minus x1 square, the potential energy in the spring. So you know x2, you know x1, x2 minus x1 you know. So initially x1 is 0 and x2 is 0.2. So 0.2 is the displacement, 0.2 meter displacement. So substituting that, half into 150 kilonewton per meter square, so k, and into x, so 0.2 square. So this will come out to be 3 kilojoules. Or we can solve it by this, the top portion of the triangle, denoted by 2. So that is the work done on this spring. So that will be coming out to be 3 kilojoules. So the other way of calculating is your piston is moving by volume delta V. So delta V is 0.05 into the work done. Initially, how would you calculate this? You can use the spring you can use this relation half kx square to find out the work done by the spring. And the other is the piston is moving by force P, 200 kilopascal. So 200 into delta V. So you can use that to find out the work done by piston. So the net work will come out again to 13 kilojoules. So this state 1 is the work done on the piston, and 2 is represented by the work done by the spring, done on the spring. Any doubts? If you have any doubts in the previous problem also, you can ask. Okay, then I think I have covered what I have prepared for today. If you have any doubts, you can ask, or else we can wind up. Then. Thank you. Okay, thank you. Then I'll be uploading this thing. You can refer it later.